Good afternoon, everyone. My name is Tom Simchak. I'm the Energy Storage Association's Research and Programs Director. Thank you for attending today's webinar on energy storage plus energy efficiency. All meetings and teleconferences of the Energy Storage Association are held in accordance with our antitrust guidelines. We ask that you abide by these guidelines during today's webinar. The full guidelines are available in the members-only area of the ESA website. This webinar is being recorded and will be available on www.energystorage.org. Questions can be submitted at any time throughout the webinar via the chat box in your browser. And following the webinar, you will receive a brief survey regarding today's topic and topics for future webinars. Your feedback will ensure that ESA continues to provide the highest value information to you and your organization. If you have any questions or interest about ESA membership, if you enjoyed this webinar, there are plenty of others, some of which are for just our members, and numerous other benefits, reports, and studies that you'll find very interesting for the energy storage world. You can contact Richie O'Neill at the email address you see on your screen. Before we get started, I'd also like to note two upcoming ESA events. Our annual Energy Storage Policy Forum here in DC at the Press Club on February 13th. Details and registration are available on the link on your screen. You can also find it on energystorage.org on our events box towards the bottom right of the main page. And also a week from today, we have a members webinar on energy storage developments in Hawaii, which non-members can also join for a fee. Likewise, you'll find that in the energystorage.org in the events area. Today's webinar is the inaugural event in ESA's storagePLUS network. storagePLUS highlights the ways that energy storage can optimize and enhance the development of other flexible or inflexible energy resources. This is the first of several webinars this year that will examine the benefits and opportunities of deploying storage alongside a range of other energy technologies. We'll be following this webinar with an issue brief discussing the synergies between storage and efficiency, and we'll do the same for future storagePLUS webinars. Let us know if you have interest or thoughts on those future webinars. Happy to get that information out to you, and we'll be conducting some research and writing on those topics. So today we'll be hearing first from Chris Perry. He's a senior analyst in the Buildings Program at the American Council for an Energy Efficiency Economy, or ACEEE. He'll be giving us something of a broader overview of storage plus efficiency issues. He'll be followed by Jeremy Twitchell, who is an energy research analyst at Pacific Northwest National Lab. He'll discuss some of the ways energy storage can be used to improve the efficient operation of the electricity grid. And lastly, Lynn Abramson, president of the Clean Energy Business Network, will offer some of her reactions as a respondent and kick off the Q&A. So thank you for attending today's webinar. Please use the chat box for any questions you might have during the course of the presentations, and we'll address those in the Q&A session at the end. So with that, I will turn it over to Chris for his presentation.
All right, great. Well, thank you, Tom, and thank you to ESA for the invitation to speak on this topic also. So, like Tom mentioned, I will be talking about energy storage and energy efficiency, some of the synergies we've seen between these two, often seen as separate, kind of siloed components of the energy system. So what we're going to be talking about, give a little background and frame the conversation, talk about some of the opportunities we see, or more or less benefits of energy storage, talk about some of the program approaches that we are seeing currently, and give you some conclusions from our research. All right, so quick who I am. My background is in energy efficiency. We, ACEEE, as an organization, we care about energy efficiency. In particular, for me, it's in buildings. We haven't spent nearly as much time in the energy storage space, but we recognize this as an important topic that we want to become more involved in. And so as part of that, we are releasing our first research brief on this next Thursday, and we will be also having a webinar, and I will remind everybody at the end about this again, but it's part of our ongoing Emerging Opportunities series. And so next Thursday we're going to be talking about this, as well as integrated building systems and new financing models. So I will encourage everybody to join us for that and get on our email listserv. So as part of our research, we looked at thermal and battery storage with a focus on commercial buildings. These seem like the top two types of storage that we wanted to explore. So thermal storage, quick background, could include cooling, chilled water, ice storage. For example, you make ice during off-peak hours and use to cool the building, or use for refrigeration during peak load times. Alternatively, battery storage, it's increasingly being used to store energy from renewable sources. Right now it's primarily lithium-ion is the chemistry that's in use. It's relatively well balanced, but other chemistries could pull ahead over the next 5-10 years. We don't really know at this point, but when we talk about battery storage, primarily we're talking about lithium-ion. There's obviously a number of other types of energy storage. Water heaters are increasingly being looked at as a way to store energy in a residential setting. Flywheel pumped hydro might make more sense at a utility scale. These are all great storage options. They're just not what we looked at for this research, so we're going to be mostly focusing on commercial and occasionally using residential as an example. And one of the ways that this ties in nicely with some of our other work on smart buildings is that energy storage software can help integrate energy storage into existing building systems, which we see as something that's important to do as more sensors and microprocessors are inserted into basically all building equipment. So a way that this could be used for energy storage is if the utility says, okay, we have a demand response event, and then that's sent to a commercial building. The building can use software to determine how can we best optimize our response for this demand response event. And so, if there's enough notice, you can pre-cool the building ahead of time. If it's in the moment, you could choose to disable EV chargers or discharge batteries, dim the lights, use some combination of all of those. And that's something that really more as we continue with this technology, it's going to be managed entirely by software and to optimize what's best for the grid, but also what gives the end user the biggest benefit, usually the monetary benefit. All right, so let's go into some of the opportunities or benefits. So we, for simplicity, have been characterizing energy storage benefits in 3 different ways. We call it grid flexibility, energy efficiency, and resiliency. And for this presentation, we're going to put a little bit more weight on energy efficiency just because that's kind of the theme of what we're talking about. That's also ACEEE's bread and butter. Just to quickly touch on grid flexibility. So when we talk about this, it's basically the term that we use to describe any benefits to the grid. And we're not trying to coin a new term. This kind of seemed like an all-inclusive way to describe it. So if you look at the left graphic, most people on this call are probably familiar with California's duck curve. Too much solar PV generation at noon, and then as the sun starts going down, 5, 6, 7 p.m., there's this steep ramp on demand for energy on the grid, which can be really burdensome to the grid. That's something that energy storage can really help reduce the severity of this ramp, which is becoming a much more of a problem for utilities. And many of you have also probably seen the graphic on the right, too, that Rocky Mountain Institute put together. I think it was from their 2015 report on the economics of energy storage. It just basically shows the different benefits of batteries to different stakeholder groups, to the consumer, to ISOs, to utilities. And they define them all different ways. For example, energy arbitrage is the purchase of energy when the price is low, sale back to the grid when the price is highest. Frequency regulation ensures generation matches the load frequency, mitigates spikes and dips. The point of all this is there's a lot of different benefits to the grid. I think Jeremy might go into a little bit more depth on some of these. It's not really going to be the focus of what I talk about, but wanted to acknowledge it. So let's get a little bit more into some of the overlaps that we've seen with storage and energy efficiency, which we found fascinating tie-ins with our work. So we saw two main ways that thermal energy storage can enable energy savings. And again, to reiterate what we've already talked about, there are obviously demand benefits to thermal energy storage. You know, you chill water at night, or you create ice at night, and then use when the demand price is low, and then you can use it when the demand price is high during the day. But in addition to those demand benefits, there's also the benefit that you can potentially downsize your equipment by using storage. So the reason for that is thermal energy storage allows you to cool the water temperature down to a lower temperature than you would otherwise. So if you're creating ice, then the ice storage allows that the water circulating through the system to be colder than it normally would, creates this greater temperature differential between the chilled water and the space temperature, and it enables potentially as much as a 50% reduction in the size of chillers, pumps, fans to cool the building down. You just don't need as big equipment to achieve the same results. And we did a quick back-of-the-envelope calculation. If you took an 800-ton chiller and were able to downsize it to 400 tons, just in energy savings, you would save $40,000 each year. So we see that as a potentially huge benefit of thermal energy storage. And the other one, thermodynamics, kind of makes sense intuitively. If you're going to be running a chiller at night, like the figure on the right, air-cooled chiller system, if it's taking in cool air at night, it's going to have to work less hard to cool it down than if it were doing it during the day in the middle of the summer with the warm air. So it also achieves substantial thermodynamic efficiency as well. So that's for thermal energy storage. We also saw benefits with battery storage, particularly when it's paired with like combined heat and power, or a lot of people call them cogeneration systems. So the way that these systems work, a cogeneration system, it's typically achieves max efficiency between like 50 and 75% capacity. Running it there, you get the optimal electrical efficiency, and it also has a high rate of heat output. And that's the whole point of a cogeneration system. You generate electricity with it, and then it produces heat, which can then be used for something else, to heat water or used to heat the building. So you're not wasting all of that heat energy. So when you pair that with a battery, it allows you to run the system at that optimal point, you know, somewhere between 50 and 75%, to charge up the battery, and then you can turn the system off. And you can compare that to how you would normally run the system, which would basically just be going up and down to meet the load. So it would be, you know, 20%, 50%, 100%, back down to 20%. And so you're never really going to achieve that peak efficiency like you can when you're just charging a battery. And so one study from, I think it was a 2012 study from out of Newcastle University, published in a peer-reviewed journal, it showed that it can improve system efficiency by as much as nearly 50% overall. Granted, that's just one study, but 50% is quite a big improvement in efficiency. And finally, resiliency. We can dedicate an entire talk to this, but we just wanted to acknowledge that batteries in particular can help buildings with resiliency during, you know, disasters, keep hospitals open, keep grocery stores from losing a lot of their inventory. So that's the final benefit. Let's talk a little bit about the program approaches that we're seeing. So this is by no means a comprehensive list. We're going to go through a few slides here with different programs and compare them, but this is to give everybody on the call a sense of how programs are looking at energy storage right now. So on the simplistic end, NYSERDA has a program where they offer free technical assistance and support for energy storage projects. This could be, the feasibility of a project, the sizing, the cost, just helping a building determine, is this something that I want to do? I will insert in here that I was talking to somebody last night that works with NYSERDA, and he was under the impression that they are rolling out, or maybe they have recently rolled out, a new, more comprehensive program. If that's the case, then feel free to send me more information about that. I just wanted to put that on the record that NYSERDA seems to be doing more than just technical assistance, but I'm not entirely sure what that is right now. So on the other end of the spectrum from technical assistance is the complicated California PUC Self-Generation Income Program, SGIP. This program has existed for a long time, since 2001. It was primarily solar then. It was restructured in 2017 to include more solar and storage, because California realized it would be a lot more beneficial to their grid if they paired them both together rather than doing just solar. And the way this program works is it uses a lottery system where winners of the top tier of the lottery get so many cents off per kilowatt hour, or per kilowatt, I guess, saves, say 30 cents, and then once that tier runs out, the next tier gets maybe 20 cents. So it's a little bit more complex. So these next programs that we're going to compare are all pilot projects right now, and they range. What I was hoping to compare with these is how the ownership differs between the utility and then the end user. So for example, Con Edison on the left installs, they own, they manage the battery, and they have full control over it. And so the user of the battery, or the commercial building owner that has the battery in their building, is able to use it as backup storage, but it's really mostly at the discretion of Con Ed when that is. If you look to the other end of that, the other end of the spectrum, Southern Company has a even 50-50 split for the residential pilot program between the utility and the customer. This is part of their Smart Neighborhoods program. And so that means 50% of the battery will always be available to be used by the customer as backup, and 50% of the battery will always be able to use by Southern Company to benefit their grid. And then Green Mountain Power in the middle has a different program approach. Also, it's the buy your own battery program. It's like a BYOB program. The customer purchases it and then signs a contract with Green Mountain Power and says you can have access, during peak events to use my battery. So it's a range of different program types. One more I wanted to mention was Electra. Electra is located in Canada, in Ontario, I believe, and they are experimenting with software to maximize the customers' the money that they can make from using their battery, and I've heard that they're also exploring blockchain as an option too. So there are many innovative things that utilities are working on right now. I'm about out of time. First of all, I wanted to apologize for all the text on this slide. It's kind of an eyesore, but I wanted to give everybody the takeaways and recommendations that we had from our research paper. The top three on this are talking about the high upfront costs of storage technology still right now, and some ways to mitigate them. Energy storage as a service can be one way. Improved rate structures, like using daily peak charges instead of monthly, can help give customers a little more options, or better forecasting would also help that. I wanted to mention that there's still some safety concerns. It seems to be mostly concentrated in New York City right now. So battery manufacturers can help mitigate that. And another recommendation is to improve sizing, because customers don't want to have an oversized system where they've wasted their money, or an undersized system that can't meet their needs. And so that's it for me. I wanted to thank everybody for joining and remind you that we have a webinar on energy storage and other emerging opportunities February 7th. And as far as our conferences, come to Hot Water Forum. I'm in charge of that. It's all about water heating, and we would love to have you there if you're interested in the topic. So with that, I'll turn it back over to Tom.
Yeah, thanks so much, Chris. That was really great. Next, we'll be turning to Jeremy Twitchell, who will drill down a little bit more into the detail of how energy storage can be used to improve efficiency on the electrical grid. Jeremy, all yours.
Great, thank you. Can you hear me okay?
Yeah.
Okay, great. So my name again is Jeremy Twitchell. I'm an energy research analyst at the Pacific Northwest National Laboratory. I'm actually pinch hitting today for my colleague Patrick Balducci. He's our chief economist here at the lab. He is the brain behind a lot of the work I'm presenting today, but he was unavailable today, so I'm here in his place, and I will do my best. If you know Patrick, then hopefully I can live up to his standards. The next slide, please. Okay. So the work that I'm presenting today, this was funded through the U.S. Department of Energy, through the Office of Electricity's Energy Storage Program under the direction of Dr. Imrajuk. They funded all the research that I'll be sharing today, and we're grateful for their support. Okay. So the agenda first, I'm just going to provide a little more background about the energy storage program that we work on. And then I'll talk about a couple of specific applications for energy storage for efficiency from a grid operations perspective. We'll look at conservation voltage reduction, we'll look at spinning reserves, and then wrap things up with a few final thoughts. So the energy storage program, it comes out of a Department of Energy report back in 2013 that identified 4 key barriers to energy storage. You know, the need for competitive energy storage technology, validated reliability and safety, an equitable regulatory environment, and finally industry acceptance, you know, making sure that utilities, grid operators understand how storage works, how to optimize it. And so that's how we're set up. I work on the equitable regulatory environment, so we do a lot with regulatory barriers to energy storage, planning barriers to energy storage. Patrick works in the industry acceptance program, which helps utilities understand how these devices work, and that's where a lot of this work today came from. There's just a quick overview of the energy storage program and where we're engaged. We have regulatory engagements where we're lending technical assistance to states. We have demonstration projects that we're doing with utilities, university partners that are helping with research. It's a very widespread program, as you can see. So when we're talking about the energy storage applications, the energy efficiency applications for storage from a grid perspective, really what we're saying is that you can deploy energy storage in a way that will reduce overall energy consumption and displace the need for additional capacity, free up existing capacity to displace future capacity needs. And so 2 specific examples of that we're going to talk about today are voltage management, which is actually 2 parallel services, volt-var optimization and conservation voltage reduction, and then using storage as a spinning reserve. But before we dive in, I wanted to throw this slide up to just keep in mind that optimization of an energy storage device is key in deploying it. So if you want to really understand where cost-effective opportunities for energy storage exist, you need to understand beforehand what the value streams are, what your device's capabilities are, and you need to analyze beforehand exactly how that device is going to perform given the value streams that it sees, so that you can know where to optimally set the device and how to optimally dispatch it to take advantage of all these services. Because as you can see, as we're layering in these different services, the way that the device is dispatching is fundamentally changing. So voltage management, the basic idea here is that our national standards allow for a distribution line to be operated within plus or 5% of its nameplate rating. So for example, your standard 120 volt distribution line can be safely operated anywhere between 114 volts and 126 volts. And the idea is that if you can operate it in that lower range, between 114 and 120, there'll be less energy flowing over the line and therefore less energy being consumed by end users. And so storage can do 2 things that really help you optimize your distribution system around this paradigm. So the first is volt-var optimization. We're getting into some complex engineering topics here. I am not an engineer, so I will intentionally keep it high level. But the idea here with volt-var optimization, or VVO, is that your storage device is injecting real power into the line, reactive power. And what that does is it improves voltage in your power factor so that you've got less current flowing over the line. And when you've got less current flowing over the line, you have lower line losses, and you're also freeing up upstream capacity, because when your upstream generators don't have to provide that reactive power, they can generate more real power. The second point there, conservation voltage reduction. You're doing the opposite here. Instead of injecting that reactive power, you're absorbing that reactive power, and you're keeping that voltage within that lower range, under 120 volts. And what that does is that your end-use devices that are consuming voltage, all your household electronics, your appliances, they're going to be pulling less current, less energy off the grid. And these are opposing services. On one end with VVO, you're injecting reactive power, and on the other end with CVR, you're withdrawing reactive power. So you really need to understand what the conditions are on the distribution feeder that you're looking at. What are the needs? And it does require some dynamic optimization, because during one moment you may need to be injecting reactive power, and in another moment you may need to be withdrawing that reactive power. And then just a final note here, that this is an inverter-based service. We're not really drawing on the battery itself to provide the service. We're using the inverter. So really, any inverter-based device is going to be capable of providing these services to some degree. So how do we quantify those services? So we're talking about two value streams here. First, when you're providing volt-var optimization, you're freeing up that upstream capacity. So you can see on the diagram there that when you add the energy storage device to inject local reactive power, the total need for your system reactive power from your generators falls. And so you can see that P rail line to the right of that graph is the freed up capacity that can now be used to serve capacity needs instead of providing that reactive power. And we just quantify that in simple dollars per kilowatt. And then the other value stream there, reducing energy consumption, again, as you're lowering the voltage, your voltage dependent appliances are going to be drawing less currents, thereby drawing less electricity. And so the total amount of energy that's flowing over that line is being reduced while you're still maintaining a constant level of service. And we just quantify that reduced energy consumption in dollars per kilowatt hour. So, example findings. So we've looked at CVR at a few sites. We've looked at it at 6 sites in the Pacific Northwest in particular. One of those sites I'm putting up here is Portland General Electric Salem Smart Power Center. And what you'll see here is fairly common amongst all the sites we looked at is that, VVO and CVR, they're kind of workhorse services. They're not high-value services. There are much more valuable services that the battery device is going to pursue. What we find is that they're reliable services. Anytime that the battery isn't performing another function, there isn't a higher value service available, it can default back to VVO and CVR because that service is always in need. And for at least a few minutes in every hour of the year, that's what the device does. And so you have this small but steady stream of benefits flowing up from VVO and CVR. And if you look closely at the costs and benefits on the right, you can see there that that little bit that we got from volt-var optimization and CVR was enough to push this project over to the top in terms of its cost-benefit analysis. And again, as I mentioned, we've looked at this in 6 sites in the Northwest. We've only found value for VVO and CVR at 3 of those sites. The caveat to that is that the Northwest has had very active energy efficiency standards for years now that have already incented utilities to engage in CVR. So there's not a lot of low-hanging fruit here. There could potentially be a lot more value for these services in other regions and other feeders across the country. But in this particular project, we did find that the device was able to reduce load on that particular feeder by about 1%. And just the key takeaway here is that these services, volt-var optimization, CVR, they increase in value the closer you can put them to the load, and that's really what sets storage apart from your traditional generation resources. You can't site a power plant close to load, but you can put a storage device close to load, and that ability to inject that power or withdraw that power closer to load makes it much more valuable. So second service we're going to talk about today is spinning reserve reduction. I think everyone here is probably familiar with the spinning reserve. There on the chart to the right, we basically have 3 levels of reserves that happens in the event of an outage. You've got your frequency response reserves, which are the ones that come on immediately, usually shorter duration, 10, 15 minutes. And then you've got your spinning reserves, which are designed to, required to be online within 10 minutes. And then those basically provide the bridge to your longer term, your operating reserves, basically providing the bridge to allow your backup power plants to come online. Specific requirements for spinning reserves in terms of how much you have to have, how long they have to be able to operate are really going to vary by region. But it's important to remember that even though we call these spinning reserves, this is technology neutral. Really, any device, any resource that can respond within 10 minutes and discharge for usually an hour to 2 are the standards is eligible to provide this service. So how storage fits here? So, traditionally, we call this spinning reserves because the idea is you had power plants already on and active and connected to the grid, but operating at a lower capacity. Their turbines are already spinning. But that always-on nature has some significant costs. You're incurring startup costs for the plant, and you're consuming fuel even when you're just in standby. Even if you're never called on to provide the service, you're still consuming fuel to keep that turbine spinning. So storage can meet that 10-minute standard quite easily, and most devices are capable of meeting that 1 to 2 hour duration requirement, again depending on the region. And there's really no variable cost while they're on standby. But the challenge there is that if you commit your storage device to provide a spinning reserve, it's locked into that service. You can't commit to provide a spinning reserve and then say, oh, well, frequency response turns out to be more valuable, so I'm going to go do that instead. So you really need to have a model that can identify beforehand what your high value services are, when they will be provided, so that your storage device is only providing that spinning reserve service when there's not a better option available.
Jeremy, very quickly, we just had a quick question on the Q&A box. What time period does the graph of PGE Salem cost-benefit analysis cover?
I might have to follow. I want to say it's a 15-year, but I will have to follow up with you on that. I do not remember the time frame off the top of my head.
Thanks so much.
Yep. So spinning reserve. So example findings here is the lab, we were asked to do analysis of what's called the hydro battery that Shell North America put together. And really what it is, it's kind of a modular pump storage facility. It's a 5 megawatt, 30 megawatt hour battery that's basically just built on the side of a river. They build the reservoir on a hill above a river, and then they just have a penstock that goes down into the river and takes its withdrawals out of the river. So we looked at that device and said, what does it look like if it's deployed in California or New York? We looked at a few locational marginal prices in each. And then we looked at Hawaii and the Pacific Northwest as well. And so, one important takeaway here is that, the value spinning reserve is very, very regional. It's going to depend on what the local requirements are by your reliability coordinator. It's going to depend on how the market compensates you for that service. And, spinning reserves, similar to what we were talking about, Volt, VVO, and CVR, it's not a high-value service, but when you can provide that, when you can use it as kind of a fallback service, it can make a difference. If you look at those 2 facilities in New York that passed the cost-effectiveness screening, Millwood and Hudson Valley, spinning reserves were the difference in those cases. If the device had not been able to provide that service, if we hadn't been able to find those opportunities, those projects would not have penciled out. So again, it's not the killer app. It's not a high value service, but under the right circumstances, it can make the difference between a project that is cost effective or not cost effective. And then just finally on spinning reserves, I wanted to point to an anecdotal example. So in April of last year, Hawaiian Electric filed a request with their regulators for a 100 megawatt, 100 megawatt hour battery. And the utility said that this device would allow them to displace the spinning reserves that they're currently providing with oil-fired generators, increase their ability to integrate renewable resources, generate savings for customers about $1.90 per month. And then the intriguing thing about this in bold there is that the utility said that the avoided fuel costs for maintaining their oil-fired generators for spinning reserves alone would pay for this project. This is still being reviewed by the Hawaii PUC, so we'll see the outcome there. But it's a really interesting case. Essentially, what HECO is saying, you can see there on the right how dramatically their daily load shape has changed just in the last 6 years. From 2010 to 2016. And HECO is basically saying, like, the previous paradigm of having quick responding frequency reserves, and then intermediate spinning reserves, and then longer duration operating reserves, that doesn't work for us anymore. We need reserves that can come on quickly and then stay on for a more extended period. They're essentially blurring the line between the frequency reserve and the spinning reserve and saying we can use a battery to provide all in one. So this is a really interesting case, mainly because I'm not aware of any other project anywhere in the world, really, that is justifying itself based purely on avoided fuel costs for spinning reserves. So we're closely watching that outcome. I think there's going to be a lot of lessons to be learned from that proceeding. So just final thoughts here. So energy storage can provide tangible benefits to the grid from an energy efficiency perspective. It can lower energy consumption, and it can reduce capacity needs. But to maximize those opportunities, you really need to understand what those values are and where those values are on the grid. You need to be able to optimize your device from a locational standpoint and from an operational standpoint. And so you really need detailed models beforehand to understand where those value streams are and what kind of device will allow you to maximize those. At the lab, we've developed a lot of granular tools for analyzing energy storage. Other entities have been doing that as well. And while these tools have been focused on energy storage, it's important to remember that they have a bigger role in that. Really they can be used to analyze, to do more granular analyses of energy efficiency, of distributed energy resources, because really what we're asking is, how do we look at the grid more granularly? How do we look at the grid on a locational basis? How do we look at the grid on a sub-hourly basis? And how do we use these flexible, scalable devices and services to optimize the grid? And I have a couple slides there at the end for additional resources about the energy storage program and a few of the reports that were cited here. But I appreciate the time. Thank you.
Excellent. Thanks so much. Really interesting, and I'll certainly going to be digging into some of your resources and endnotes. It's a really interesting area and really a lot of great benefit for the energy storage sector. So now we're going to turn to Lynn Abramson as a respondent to offer some thoughts and reactions and start off the Q&A. Lynn, all yours.
Great. Do you hear me?
Can, yes.
Excellent. Great. Well, thank you so much, Tom, for inviting me to participate. Thank you also to Chris and Jeremy for the really fascinating presentation. Before I respond to some of the themes that I heard today, just give you some background on our organization and our perspective, as I think that might be instructive in understanding the ways we are looking at the cross-sections of efficiency and storage as well. So our organization works to grow the clean energy economy through policy, public education, and business development assistance for energy companies. We are a small business-focused division of the Business Council for Sustainable Energy, which is a coalition of some of the leading sector-specific trade associations and corporations working across the clean energy economy in renewable energy efficiency, natural gas, storage, and others. And I'm happy to say that Energy Storage Association is one of the members. We have a little over 3,000 members across the nation in all 50 states, nearly 350 congressional districts. and a diverse spectrum of technologies. I'll just note there that efficiency and storage are very high up among the list of technologies represented by our membership. And so the issues that we're discussing today are very important to us. Our parent organization, the Business Council, partners every year with Bloomberg New Energy Finance to release data looking back on prior year trends and also the prior decades trends in the clean energy economy, and just highlighting that the next edition of the fact book will be coming out on February 13th, so stay tuned for that. You can find it on bcse.org. And there is a lot of discussion about trends in storage and the intersection between storage and other technologies in that data. Additionally, we produced a partner project called Faces Behind the Facts, which is examining some of the business leaders behind the trends reflected in the fact book. And we look at both very small businesses as well as some leading corporations and utilities, and really try to humanize the stories of the clean energy economy to make them accessible to the lay audience, to public and public policymaker audiences. And we do welcome ideas for new projects to feature, so please contact me if you're interested in learning more. This is our website, cebn.org, and I urge you to check it out to learn more about us and to stay tuned for the fact book and the Faces release. But now I want to react to some of the themes that we heard from the speakers today. And before we turn it over to the audience Q&A portion, I have a few questions to kick off the discussion with our speakers. So one of the themes that struck me was the discussion on conservation, both at the building level as well as in the grid level. And we're all familiar with the old adage that the cheapest energy is the energy you don't use. But I think that that value of conservation is often overlooked and in discussions about the United States energy sector. And so I'm really glad that the Energy Storage Association has decided to focus on these complementary technologies of storage and efficiency that do share that common benefit of reducing the need for new generation, avoiding the need for overcapacity, and just enabling us to create new energy by being smarter in how we use the energy we already have. And I'm also struck by, in the presentation, some of the case studies that both Chris and Jeremy raised, the growing sophistication we are seeing in the hardware and software that's making these kinds of transformations possible, as well as the business and financing models. In particular, that case study on Hawaii that Jeremy presented. These are very sophisticated new ways of managing our systems to improve energy reliability. And I see that this really reflects a trend in growing customer awareness and utility awareness and demand for reliability. At the customer level, we see this in critical facilities such as hospitals and military bases and campuses, along with commercial customers for whom even a temporary loss of power can be devastating. And an example of that could be data centers. But then at the grid level, we've seen how important it is to better regulate voltage and really manage our grid as efficiently as possible. So Jeremy and Chris touched on this issue from different angles, with Jeremy focusing more on the grid management and Chris more on the building level. But it really demonstrated how storage can enhance reliability and efficiency can help regulate load, and these are very complementary, complementary benefits. And then finally, I was really struck by the theme of connectivity, which is the central point of this webinar series. And we're looking at connectivity across technologies, in this case, this intersection between building efficiency, grid regulation, and storage that's making it possible to regulate load and supply in new ways. But I am observing and hearing this trend from many of the technology and service providers that we work with, that increasingly we're seeing more and more projects that are combining multiple technologies in new ways to optimize performance. So instead of just solar, we're seeing solar plus storage plus combined heat and power. And some of the case studies we heard about today are really reflecting that trend. I'm also struck by the theme of connectivity when it comes to partnerships that are needed to make these transformations possible. And just that map that Jeremy showed in this presentation of the national labs, universities, and regulatory bodies that are all being engaged by the Office of Electricity's Energy Storage Program. That just speaks to how important these partnerships are. We need government support at the federal, state, and also the utility level. We need the academic research to innovate new technologies. We need private sector innovation. And working together throughout this landscape, that is how we're going to promote the continued evolution of the U.S. energy economy. So those are some of the themes I took away from today. I'm really looking forward to hearing the rest of ESA's webinar series on this topic and appreciate the remarks from our presenters. So I'm going to kick it off with a few questions for our presenters, and then we're going to turn it over to the audience and open it up for further discussion. And I would just encourage Tom, Jeremy, and Chris to just jump in in responding to these and make this a discussion. But you all highlighted some examples of case studies that you have encountered, but I wanted to talk further about what kinds of customers are most likely to be the early adopters of efficiency and storage applications, and what is motivating those decisions?
Well, this is Chris. I can take a crack at that one first. In our research, we saw, I think it was from NREL, they found that the rate structure was one of the biggest determining factors for cost effectiveness. And it was a threshold of like $15 per kilowatt or greater that made energy storage cost effective. So I think your first adopters are going to be the people that really see the most economic benefit from it, and they're going to have a lot more incentive to do it right away, whereas I think maybe like the resiliency benefits might follow or might be secondary. But that's just my initial perception. Jeremy might have a different opinion than that.
Yeah, so I think the answer is it depends. One important thing that we've seen in the early phases of energy storage is policy matters. When you talk about energy storage providing ancillary services, for example, the leader there was PJM, I guess really FERC, telling market operators you should pay these ancillary service devices based on how quickly and how accurately they respond, pay for performance. And that just unleashed a huge opportunity for energy storage. And you had all this energy storage come into PJM and displace a lot of capacity. I don't remember the exact amount, but I want to say it's somewhere around 400 megawatts of capacity that was displaced from ancillary services to go provide capacity, and these storage devices that were providing these ancillary services frequency response much more quickly and capably. On the flip side of that, just kind of building off the discussion about behind the meter energy storage, the big challenge we see there is, a customer can deploy energy storage for reliability, a utility can help a customer deploy energy storage for reliability, but we don't really have a way of valuing reliability. So, if we did one analysis, for example, where a utility deployed energy storage to help a large industrial customer improve their reliability, and that customer derived significant benefit from that, but it raises the question, this was kind of a pilot project, but it raises the broader question of who pays for reliability? Does the utility pay? Do customers pay? What's a fair cost share? There's a lot of questions that remain there that I think there's going to need to be some policy and regulatory discussions about how do we value these services and how do we assign their costs.
I'm glad you raised that, because that's exactly the question I was going to pose back to you in terms of who pays for reliability. I think that's a really interesting question. And you talked in the sense of grid reliability and how do you, just manage grid voltage optimization, reduction, spinning reserves. You discussed some of these drivers for storage and efficiency. But the question is, what drives some of the movement in that direction, some of the specific markets in which you see that grid reliability asset being monetized? And you did speak to the importance of policy. So I'm wondering if you could just elaborate further on where you see this grid reliability asset being monetized, and also how utilities are working to recoup that cost from their ratepayers.
Well, I think you're kind of on the leading edge there. Especially with all the conversations we've been having lately about resilience. Storage can be incredibly valuable in resilient applications, but we don't have any kind of metrics for valuing resilience. We don't measure resilience. We don't pay for resilience. And absent some kind of structure for how those investments are going to be made, it's really difficult to figure out who's going to make them and to really plan. We don't really plan a grid for resilience. We don't really plan for local reliability. We plan for system reliability, but some customers value a higher reliability than that, and we've seen some customers making those investments. But when you're talking about the bigger picture, about the underlying policies that need to be developed, I think you're still very much on the leading edge, and I don't have a whole lot of answers for you.
I will agree. I will agree with that it's on the very leading edge. I keep putting in plugs for NREL's research, and I'm going to do it again, but they have just started looking at how to quantify resilience, and the way that they've been doing it is like losses, like economic losses from grid disruptions to businesses. And they have kind of like a preliminary paper out on that. I think they want to do more work on it, but that could be an avenue in the future if they determine that this is the best way to quantify it.
And in that
I honestly wouldn't be surprised. Sorry.
So I would say in that future you can stay tuned for a Energy Storage Association webinar on storage plus resilience later this year.
Oh, very exciting. It's a timely topic. And I was going to say, I feel like we might see the military really being at the leading edge of working on that. Chris, I wanted to ask you, too, if you can elaborate more on some of the innovations you're seeing in utility rate design. You talked about a few, but just broaden that a bit, that where you're seeing true incentives for efficiency in storage, and what are some of the common elements?
Well, I might sidestep that a bit and talk a little bit more about program design to incentivize energy storage. And so what I've seen and what I think needs to be done is a lot of times there's like a kind of an arbitrary limit on the size of a system. So incentivizing a system that's like 100 kilowatts. And part of our research was talking to people who install these systems, and they say, look, there's a lot of benefit to be had from smaller systems, 5, 10, 25 kilowatt. And so maybe expanding, this isn't so much rates, this is more like what a utility can do, but if they can expand their program to be more inclusive of all different types, in the aggregate, all of energy storage in all these different buildings adds up and can really save a lot of demand and really help the grid out.
This is Tom. I might actually interject here to segue to a question we've had in the Q&A box. Brian Kaufman asks about whether energy storage is participating in utility EE programs as an approved mechanism to reduce demand. If not, why not? If a storage device can commit to permanent reduction in load. I might sort of start off with one example and maybe pass to Chris or others if there are particularly good stories to tell there. In the Farm Bill passed into law in December, energy storage was added to the list of eligible technologies in the Rural Energy Savings Program, which is a program designed to support rural utilities in providing low-interest loans to farms and small businesses mainly. Now energy storage can be a part of that. That was just passed in December, so I'm pretty sure no utilities actually pulled it off yet, but something to watch in the coming months as that opens up the opportunity for storage in efficiency programs. Do any other folks have examples of utilities combining storage into efficiency programming?
Yeah, real quick. I didn't know that about the Farm Bill, so that's interesting. I'm going to look into that. I saw Brian's question come in. I think it's a really great point, and it's something I wish I had a little bit more time to go in my presentation. I think the best example that I've seen is Southern Company with their Smart Neighborhood program. It seems more of a holistic, granted it's residential, not commercial, which was our focus, but it's a holistic look at connected neighborhoods, microgrids, storage, energy efficiency all together in these new developments. I think the short answer to his question would be it's not happening nearly enough. Like, are people, do you get incentivized if you are installing a cogeneration or a combined heat and power plant system to also add battery storage to that because of the synergies between efficiency and demand? Not that I've seen yet, but it's something I think we should push for.
Yeah, just one thought on that. So most energy efficiency programs are pretty broadly drawn. They're not usually prescribing a list of measures. Rather, it's the utility coming to the regulator and say, hey, here's what we're doing. Here are the measures that we've demonstrated to be cost effective. Some states explicitly include CVR in their energy efficiency standards, which is another potential vehicle. So I don't think the challenge would be designing an energy efficiency program that would allow for storage. I think the bigger challenge is, utilities developing the kind of analytical tools and incorporating storage into their planning in a way that will allow them to identify those opportunities so that they can go to their regulators and make the case. I think that's where the hurdle is.
Yeah, I think that's a really good point, and particularly how states or utility commissions can ensure that storage is being accounted for as a possible sort of solution in integrated resource plans and other medium and long-term planning from utilities. We've got maybe time for one or two more questions. Lynn, if you had any last question, and then if anyone on the line has a last question, please stick it in the Q&A box before we wrap up. Lynn, go ahead.
Yeah, so actually to the point we were just discussing about the analytical tools that utilities lack to really identify the storage, I'm curious, and this is an open question to all three of you, what's on your wish list in terms of are there new technological innovations in terms of software, hardware, controls, or perhaps, Tom, you might want to speak about policy signals that are on your wish list that would really help make these efficiency and storage projects more feasible. So that's a very open question. I'd love to hear from all of you about that.
Sure. I can jump in real quick and say that I think the technology out there right now is in a pretty good spot. It's obviously going to continue to improve, but the hardware is pretty good. The software is getting better every day. The enabling technology that I would like to see more of is smart meters. I mean, having like 15-minute interval data really allows a utility, or probably even more so, somebody who's trying to sell storage to a building, they can really make the business case if they have that interval data. And they can say, this is how much money you're going to save. This is the exact size battery system you need. Otherwise, you're just kind of flying in the dark and you can't really support your case.
Really more of a deployment than anything new that's needed, and that's a great point.
Yeah, nothing cutting edge, but it's there. It just needs to be deployed.
Jeremy and Tom, what are your thoughts on your wish list?
Well, go ahead, Jeremy.
Okay, I was just going to say, I work in a lab. We don't really advocate or have wish lists, but I can talk a little bit about where we're directing our research efforts and where we see the need, the information needs as we've been hearing in our interactions. So, the labs, the energy storage program, there's been a ton of work done on evaluating energy storage and understanding how it works. And so one of the areas that we're really trying to direct our research is now how do we translate those findings into planning processes? How do we really communicate what we've learned in a way that will help utilities, help regulators, help the industry understand what the values of energy storage are? How do you use a model to identify those values, and then how do you incorporate that into the existing planning process? Another area we're really looking at is storage for resilience. As I mentioned before, there's not a lot of metrics. There are no metrics there. You haven't seen a lot of investment in there, partially because of that. So one of the things we're trying to understand is, how can storage be used for resilience, and what kind of, policy and regulatory innovation are needed to unleash that potential.
Great.
Thanks so much. Well, that brings us to the top of the hour. Before we conclude today's webinar, I'd like to again mention in 2 weeks from today, we have our Energy Storage Policy Forum. 1 week from today, our webinar titled Reading into Hawaii's Energy Storage Headlines. Info on those can be found, web address on the screen and on our website. I'd also like to once again thank Lynn, Chris, and Jeremy for their participation on today's webinar, and my colleague Lexi, who's been ably steering the technical side of the system today. Thanks so much for joining us. Hope you can join us on future webinars. And if you have any ideas for future webinars, education@energystorage.org. Thanks again, and have a great afternoon. Bye-bye.